Now we will try to solve some problem. So these problems are basically from gate papers. Let's see the problem. In a simple Brayton cycle, the pressure ratio is given 8. So Rp is given 8 Brayton cycle, so or gas turbine cycle, and temperature at the entrance of compressor. So T1 is given 300, 1400 temperature at the entrance, and the, okay, this is T1, and so that means I have to draw my TS diagram. TS 1 2 3 4. So T1 is given and T3 also given 1400 K. Both compressor and gas turbine have isentropic efficiency eta isen 0.8, eta isen for both turbine, compressor both. For the gas, assume constant volume, constant value of Cp. So Cp value 1 kJ per kg given. Specific heat ratio is given 1.4. Neglect changes for kinetic potential energy. Calculate power required and calculate thermal efficiency. Eta thermal and Wc. Okay, eta thermal. Maybe I'll put Th. Now I have to calculate these two parameters. Now Rp is given 8, that means P2 by P1 is given, okay, and gamma also given 1.4. So process 1 to 2, 1 to 2 process. So what is happening? Actual compression happening, 1 to 2 isentropic compression. So 2 dash 4 dash, okay. So 1 to 2 actual process, 1 to 2 irreversible process, or energy will be lost. So for reversible adiabatic compression process, T2 by T1, T2 by T1 equals P2 by P1, gamma minus 1 by gamma. So T2 equals 300. So T1 equals 300. So T2 equals T1 into 8 divided by 1.4 minus 1, 1.4. So this value is coming 543.43 K. Okay. Now eta isentropic efficiency, eta isen. So isentropic compression work, isentropic compression for compressor. Okay, for compressor, compression divided by actual compression. Okay, so Cp T2 minus T1 W actual. Now this gives like eta isentropic given 0.8 and Cp given in the problem is 1, and T2 value we just calculated 543.43, and T1 value we know 300. Okay, W actual. So therefore W actual equals 303.75. This is the answer they are asking. Unit will be kilowatt. Now to calculate efficiency, first Q in equals Cp T3 minus T2 bracket eta isentropic W actual by W isen for turbine. So H2 minus H1, H2 dash minus H1. Okay, so 0.8 the value is given. So this will be giving 0.8 equals 543.43 minus 300 divided by T2 dash minus 300. Okay, so therefore T2 equals 604.3 K. So we got the T2 value. We got T2 dash value. So Q in equals 1 and T3 we are calculating here. T3 value we know 1400 given, and T2 value we just calculated 604.3. So this is giving 795.7 kJ per kg. Okay, and process 3 to 4, T3 by T4 equals P3 by P4 gamma minus 1 by gamma. Therefore T4 equals T3 by P3 by P4 gamma minus 1 by gamma equals 1400 divided by 8, 1.4 minus 1, 1.4. So this value is coming 772.86 K. Now eta isentropic equals W actual by W isen implies 0.8 H3 minus H4 dash H3 minus H4 equals T3 minus T4 dash T3 minus T4. So therefore T4 dash equals 898.288 K. So now W actual equals Cp T3 minus T4 equals 1400 minus 898.288. So this is giving 501.712. অতএব eta thermal equals W actual minus W actual turbine by W actual compressor divided by Q in. So this is giving 501.712 minus 304.3 divided by 795.7 into 100. So this is giving 24.8%. So this is your answer. Another problem, an ideal Brayton cycle operating between two pressure limit 1 bar and 6 bar. That means TS diagram showing this is 1, this is 6. Within that pressure limit is working. Temperature also given. Minimum temperature means here minimum temperature will be there 300, maximum will be 1500. The ratio of specific heat gamma is giving 1.4. Okay, so it will be like this. The approximate final temperature in Kelvin at the end of compression expansion process respectively. So T1, 2, 3, 4. So T2, compression expansion process. So T4 we have to find. So work is very simple actually. Here Cp by Cv given. So adiabatic condition if I apply, T2 by T1 equals P2 by P1 gamma minus 1 by gamma equals imply or 300 divided by T2 1 by 6 0.286. So this will be giving T2 equals 500 K. Now again for the process 3 to 4 process if we consider, then T3 by T4, very simple problem, this one equals P4 by P3 gamma minus 1 by gamma So from there you are getting T4 equals 900K. Okay, so this is your answer. So again similar problem, in a gas turbine cycle, hot combustion product with the specific here Cp is given 98, Cv also given. So Cp by Cv you can calculate from here, and enters turbine 20 bar and 1500 K, exits at 1 bar. The isentropic efficiency given, work developed by the turbine per kg of gas flow is, so you have to calculate work per kg of gas. So first you draw TS diagram with two pressure line, 1 to 2, 3 to 4. So 1, 2 dash, 3, 4 dash. Okay, this is given 20 bar, this is given 1 bar, lower one 1 bar. So Cp is given 0.98, H isentropic is given 0.94, eta isen 0.94. Okay, Cp given, T3 also given, T3 equals 1500, this is T3, P2, this is P2 equals P3, P1 equals P4 equals 1 bar, and gamma you can calculate Cp by Cv equals 0.98 by 0.7538. These values are given, so it is coming 1.3. Now applying general equation for the reversible adiabatic process in 3 or 4. So T3 by T4 equals P3 by P4 gamma minus 1 by gamma. So this value will be giving T4 equals 751.37. You see the previous calculations, so same way you can calculate. Okay, eta isentropic actual output divided by ideal. So T3 minus T4 dash T3 minus T4. So this will be giving 0.94 equals 1500 minus T4 dash 1500 minus 751.37. So this will be giving T4 dash equals 796.3 K. So turbine work Wt equals Cp T3 minus T4 equals, we can write 0.98, the value is given already, T3 1500 given 796.3, it is 796.3. So this is giving 698.64 kJ per kg. Okay, this is your answer. So you see another problem. In a gas turbine plant working on a Brayton cycle with regenerator. So TS diagram you draw, TS. Okay, 1, 2, 3, 4. Brayton cycle with regenerator's efficiency 75%. 75% regenerator efficiency is there, effectiveness is there. Air inlet 0.1 MPa, 0.1 MPa, 30 degrees centigrade. So T1 equals 30 degree centigrade. Pressure ratio 6. Maximum cycle temperature is given is equals 900 T3. If the turbine and compressor have efficiency 80%, both are having efficiency 80%, find increasing cycle efficiency due to regeneration. Okay, so again T2 dash 3 4 dash. Now T2 minus by T1 equals P2 by P1 gamma minus 1 by gamma equals T3 by T4 4s or 4 equals 6 0.4 by 1.4, 1.668. So T2 equals 303 into 1.668, 505. Okay. T4 equals 1173 by 1.668 equals 705 K. Okay, so T2 minus T1, T2, so better I'll write this is 2S, S. So T4 S, T2 minus T1, T2S minus T1, eta C equals 505 minus 303 divided 0.8 equals 252 K. So Wt equals first T3 minus T4 eta T, T3 minus T4 equals 0.8, 1173 minus 705, 375 K. Now Wt equals H3 minus H4 equals Cp T3 minus T4 is 1.005, this Cp value, T3 minus T4 375 equals 376.88 kJ per kg. So Wc equals Cp T2 minus T1 1.005 into 253.26 kJ per kg. Okay, so T2 equals 252 plus 303.555 K. Q1 equals H3 minus H2 equals Cp T3 minus T2. So this value is giving 621.09 kJ per kg. So eta equals Wt minus Wc divided by Q1, 373.88 minus 253.26, 621.09 equals 19.9%. With regenerator. Now we have added regenerator. T4 equals T3 minus 375 equals 1173 minus 375, 798 K. Regenerator effectiveness. Effectiveness equals T6 minus T2 divided by T4 minus T2 equals 0.75. So T6 minus 555 equals 0.75, 798 minus 555. Therefore, T6 equals 737.3 K. Or Q1 equals H3 minus H6 equals Cp T3 minus T6, 1.006, 1173 minus 737.3 equals 437.88 kJ per kg. Now W net remaining the same, so eta equals W net Q1 equals 123.62, 437.9 equals 0.2837 equals 28.37%. Percent increase due to regeneration equals 0.28 32837 minus 0.199 0.199 equals 0.4256 42.56%. So this is your answer. So thank you very much for today's lecture. Next day we will start new topic with this gas turbine thing. Thank you very much.